Section 1.3, more on functions and their graphs. Our objective for this section is to identify intervals in which a function increases, decreases, or remains constant, to use graphs to locate relative maxima or relative minima, to identify even or odd function and recognize their symmetries, to understand and use piecewise functions, and finally to find and simplify a function's difference quotient. So in this section, we are going to be doing a lot more with how functions work and with their graphs, as you can see. So let's start with this graph right here. Pretty simple graph. It talks about the average fuel efficiency of new U.S. passenger cars. Okay? And clearly, we can see that I have a trend for the blue part of the line and then a trend for the green part of the line. And we can use really basic words to try to describe both of these, like decreased, minimum, increased, steepest, and maximum. So these are all words that we should know and be able to tell how graphs are reaching these points. Okay? So we're probably familiar with these words that we use, right? Decrease, increase, minimum, maximum. In this section, we're going to enhance our intuitive understanding of the ways of describing graphs by viewing these descriptions through functions and not just through pictures, through how these functions work. Okay, so let's start with increasing and decreasing functions. Okay, a little bit of a silly example here, but it's too late for that flu shot now. It's only 8 a.m. and you're feeling lousy. Your temperature is 101 degrees Fahrenheit. And fascinated by the way that algebra models your world, and of course, that's a silly joke, you decide to construct a graph showing your body temperature as a function of the time of the day. You decide to let x represent the number of hours after 8 a.m. and f of x your temperature at time x. So if we look at this first graph, right, you woke up at 8 o'clock in the morning, f of 0 is 101. Okay? Then at 11, right, you could probably called out of school, you went back to sleep, and so you started feeling a little bit better. Okay? So if I look at this interval, right, between the hours of 0 and 3 hours later, so from 8 a.m. to 11 a.m., so if we were looking at a interval from x such that 0 is less than x and x is less than 3, on this interval, or from 0 to 3, if we're going to use interval notation, something happened. This graph was decreasing. It started high and went down a little bit lower. Okay. What happened next? So you started, you woke up probably about 11 and you started doing some activity. Maybe, you went outside, you ran around for a little bit, you did some work around the house. Whatever you did, your temperature then went back up. This point right here is important. That's the minimum of the graph, the lowest this graph ever gets. But we can clearly see that from there to here, between x such that 3 is less than x, which is less than 5. If we're looking at my x values, between 3 and 5, this graph increases. It goes up. Then you realize you were overdoing it, so you decided to just sit, relax, maybe do some math homework. Whatever you decide to do, then your temperature flattened out. Okay? So with x such that 5 is less than x, which is less than 7. So in between 5 hours and 7 hours, okay, between 5 and 7, your temperature remained constant. So I think this is pretty easy to sort of look at this picture and see what's going on. The graph is going down, the graph is going up, the graph is staying flat. Okay? But I'm sure you know that we cannot just say, oh, the graph's going up, the graph's going down, the graph is flat. We need to say that in a mathematically appropriate way. And the way we do that to tell whether a function is increasing, decreasing, or constant is to use these notations right here. So number one, a function is increasing on an open interval I, it could be any interval you want, if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So if we look at the increasing function picture right here, we're always going to have x1 less than x2, right? We always want to go left to right when we're comparing 2 points. Okay? That's how our graphs move left to right, so we want to look at our points from left to right as well. Notice that f of x1 is less than f of x2, right? As you go right, the graph outputs go up. That is an increasing function. For number two, a function is decreasing on an open interval I if f of x1 is greater than f of x2 whenever x1 is less than x2 for any x1 and x2 in the interval. So as you go right, my outputs are going down. Okay, that makes sense, right? The function is, the outputs are going down, so your function is decreasing. And to tell that a function is constant on an open interval, f of x1 is equal to f of x2 for any x1 and x2 in the interval. So no matter what the input, your outputs are exactly the same. Okay? So let's state the intervals on this function where the function is increasing, decreasing, and is constant. Okay? So first, let's do increasing, decreasing, and constant. Okay? So where is this function increasing? Well, anywhere as I go left to right, anywhere this graph goes up. So it goes up from there to there. Okay, when we're talking about increasing and decreasing and constant, when we're talking about functions, we're always going to be talking about what's happening between my x values. My f of x values, my y values, tell me what's going on. Is it increasing, is it decreasing, or is it constant? But my x values is where what I would say about the interval. Okay, so for increasing, this function is increasing from 0 to x is equal to 2. So from 0 to 2. Now the question is, on our interval notation, should we use parentheses or brackets? And we're always going to use parentheses for increasing, decreasing, and constant intervals. The reason why we don't use brackets is because if we're looking at just one point, like this point, 0, we can't say at 0 the function is increasing because we need another point to compare it to. Right? So always with increasing, decreasing, and constant, we are going to use parentheses. Now, hopefully it's clear that there are 2 places this function is decreasing. From here down to here, and from 2 down to there. Okay, because the ends of this function have arrows, that means that this function is going to continue on forever, till infinity. So we're always going to go from left to right when I read these intervals. So the furthest left this function goes is negative infinity. Right? It's going a little bit to the left as I go up here. That's just enough. It's going to keep going left and left and left and more and more and more. So this function starts at negative infinity to 0. Then when I want to put another interval together with it, I put a union symbol. And it also decreases from 2 to positive infinity. Okay? And this function is never constant. Right? It never remains constant. And you can say never, you can say nowhere, you can say whatever you want to say. Okay? Let's look at another one. So, increasing. This function is, well, whoops. Increasing. decreasing, and constant. So where is this function increasing, where is this function decreasing, and where is this function constant? So it's increasing from there, from 0 to infinity. Okay? It's never decreasing, right? Because there's never anywhere that the function goes down from left to right. And it's constant, it's flat from negative infinity to 0. Always use parentheses, always using parentheses with these functions. Okay? Next, relative maximum and relative minima. So the points at which a function changes its increasing or decreasing behavior can be used to find any relative maximum, or any relative minimum values of a function. Okay? So a function value f of a is a relative maximum of f if there exists an open interval containing a, such that f of a is greater than f of x for all x not equal to a in the open interval. And all that means is that this point right there is the highest point around all the other points, right? It's the maximum. It's the biggest the function gets in any interval. That interval can be whatever I want it to be, right? As long as that is the biggest the biggest output around all the other function, then that is a maximum. And same is true with minimum. The function value f of b is a relative minimum of a f if there exists an open interval containing b such that f of b is less than f of x for x not equal to b in the open interval. The word local is sometimes used instead of relative when describing maximum or minimum. Okay, so we can talk about that a little bit as well. Here's the confusing part. Okay, what's the difference between where a function has a relative maximum or minimum and the relative maximum or minimum? You have to be very careful with the words there. Okay, if f of a is greater than all the values of f near a, then f has a relative maximum at the input value a. The relative maximum is the output value f of a. Equivalently, f of a is a relative maximum value of the function. So the inputs are where the function has the relative maximum. The outputs are the relative maximum. And the same is true for minimum. If f of b is less than all the other values near b, then f has a relative minimum at the input value, and the relative minimum is the output value. Okay. So let's look at this picture of a sine wave. If the graph of a function is given, we can often visually locate the numbers at which the function has a relative maximum or a relative minimum. For example, this picture of our sine wave shows that the function has, here's my maximum, it has a relative maximum at pi over 2, and that maximum is 1. That is the x value, that is the y value, that is the input, whoops, input, that is the output. Okay, so always when we're talking about relative max and relative mins, the place at where the function has a min or max is the x value. The y value is the relative maximum. Okay, and we can tell that by this picture again. Now let's look at this point right here, which is a relative minimum. Okay, so the function has a relative minimum at negative pi over 2, and the relative minimum is negative 1. Notice that f does not have a relative maximum or minimum at negative pi, 0, and pi. Negative pi, 0, and pi. It has intercepts, x-intercepts, or zeros, either way. Okay, so most of those two things, increasing, decreasing, constant, and relative max and relative min, you can sort of tell just by looking at the function, okay, just by looking at the picture. Even and odd functions and symmetry comes from the equation. So the word symmetry comes from the Greek symmetria, meaning the same measure. And we can identify a function whose graph has symmetry by looking at the function's equation and determining if the function is even or odd. Okay? So if the function f is an even function, if f of negative x is equal to f of x for all x in the domain of f. That means that if I replace all the x's in the function with negative x's, when I do all the calculations, when I simplify it, nothing will change. So f of negative x is going to be the same as f of x. For an odd function, when I plug in f of negative x, everything changes signs. The entire function becomes opposite. Everything that was positive turns negative, and everything that's negative was positive. Okay? Even functions does not change if x is replaced with negative x. Every term on the right side of an equation changes sign if x is replaced with negative x with an odd function. Let's see how to do it. Let's determine if these functions are even, odd, or neither. So here's my original function. In order to tell, I need to calculate f of negative x, which means I input a negative for every value of x. Well, now we have to evaluate it. Negative x to the third power, negative times a negative times a negative is negative. Negative 6 times negative x is positive. Notice that this term was positive, now it's negative. This term was negative, and now it's positive. Everything in this function has changed signs. So this function is odd. Let's look at the next one. So g of negative x, because I want to be able to tell if this function is even or odd, so I plug in negative x, turns into negative x to the fourth power minus 2 times negative x squared. Well, negative x to the fourth power, negative times a negative times a negative times a negative, becomes positive. And exponents comes first, so negative x squared becomes positive x, and so this stays negative. And notice that this function is exactly the same as this function. So this one is even. And also notice the two exponents here. They're both even. Gives me an even function. Notice the two exponents here. That's odd. That's a 1. That's odd. So all the exponents are odd, which gives me an odd function. For h of x, if I plug in negative x, I'm going to get negative x squared plus 2 times negative x plus 1. Negative x squared turns into a positive x squared, but the middle term now turns negative, and so everything didn't change, and everything didn't stay the same, so this function is actually neither even or odd. Okay? So that's possible too. So it doesn't have to be even or odd, it could be nothing. And why we care about this is we can see what even or odd functions tell us about a function's graph. If we start with an even function, right, f of x squared minus 4, if I plug in a negative x, I get negative x squared minus 4, right, negative x squared minus, or positive x squared minus 4, so we get our original function back if I plug in negative x. If I were to graph this function, okay, it is a parabola. Here's the graph of x squared minus 4. Notice that this function is symmetric with respect to the y-axis. It's like the y-axis is a mirror. It's the same on both sides. If we have a point here, 3, 5, we also will have the point negative 3, comma 5. Okay? All even functions are symmetric about the y-axis. Okay? Always. Always. These graphs always have this kind of symmetry. Well, if even functions are symmetric about the y-axis, you would probably guess that odd functions are symmetric with the x-axis, but that's not kind of how it works. Okay, but let's see this first. The graph of an even function in which f of negative x is equal to x is symmetric with respect to the y-axis. Now let's think about an odd function. F of x is equal to x to the third power, shown in the figure below. This function is odd because if we plug in a negative x, right, we would get negative x to the third, which the only thing there, change signs. Notice that this graph is not symmetric to the y-axis, but it is still slightly symmetric. And the way I can tell the symmetry is by flipping it upside down. And if I flip it upside down, you can see that the graph looks pretty much the same as it did when it was right side up, okay, like that. Okay? So this is called being symmetric with respect to the origin. Whoops. Respect to the origin right there. There we go. Okay. Every point on the graph x, y also will have its counterpart, negative x. Negative y is also on the graph. And observe that the first and the third quadrant portions of f of x to the third are reflections to one another with respect to the origin. Okay. Notice that f of x and f of negative x have opposite signs, and all odd functions have graphs with origin symmetry. If you flip them over, they will look the same. Okay, so we covered a lot of stuff there. The graph of an odd function in which f of negative x is equal to negative f of s is symmetric with respect to the origin. All right, so we covered a lot of stuff there. Let's run through this problem that sort of brings it all together. Okay, and there is 12 parts. So the domain of this function. We got an arrow over there. We got an arrow over there, which means the domain of this function is from negative infinity to positive infinity. The range of this function, the y values. Well, we have an arrow up there, but this is flat. I can see that's not going to be going down ever. That's the lowest point on the graph right there. The graph goes through negative 4 there. So my graph goes from negative 4 to positive infinity. This graph has two x-intercepts, two places that it crosses the x-axis, which would be 1 and 7. Or I could write the whole point. I could write 1 comma 0 and 7 comma 0. It has one y-intercept, which is 4. If I wanted to write the point, that would be 0 comma 4. Now here's what we did in this section. Increasing, decreasing, constant. Where is this function increasing? Right, we're going to look at the x values. We're going to let the y values tell us whether the function is going down or going up, and I can clearly see it's going up over here. Only with parentheses, never with brackets. This function is increasing from 4 to infinity. This function is decreasing from 0 to 4, and it is constant from negative infinity to 0. Now here's what I said before, that these two can be tricky. The number at which f has a relative minimum. When I see this, right, the number at which this function has a minimum, that means the x value. So this function has a minimum at 4. And that minimum is the output, negative 4. And I can clearly say that's my point, right? 4, negative 4. This question is asking for the input. This one is asking for the output. Just like this question right here, f of negative 3 is asking me for the output at negative 3, which is 4. The values, this is the input now, right? Inside of the function right there goes an input. So these are the inputs for which f of x is equal to negative 2. Well, here's where the function equals negative 2, and here's where the function equals negative 2. So this would be 2 and 6. And is this function even, odd, or neither? Well, it's not the same on both sides of the y-axis. And if I flipped it upside down, it would not look exactly the same either. So it is neither. Okay, so hopefully that sort of clears up some of the stuff that we did at the beginning of this section. Okay. Let's move on to piecewise functions. So a piecewise function is when you have two or more parts to a specific function. So let's look at this function right here. Cell phone companies offering you the following plan. $20 a month buys you 60 minutes. additional time costs 40 cents per minute. We can represent this plan mathematically by writing the total monthly cost C as a function of the number of calling minutes T, C of T, time. Okay, so we see here 20 bucks if your time is in between 0 and 60 minutes. $20 for the first 60 minutes plus 40 cents per minute times the number of calling minutes over 60 if T is bigger than 60. Okay. And here's my graph, flat, and then it's going to cost more and more depending on how much you use it. So this is a piecewise function because it's defined by two or more equations over a specific or a specified domain, and we have rules to what we can do for each one. So let's calculate this. Okay, I can easily calculate C of 30 and C of 100. Well, I have to decide first which function to plug in the number for. So T is going to be 30 because that's what I want to evaluate my function at, which means that it's in between 0 and 60, which means I'm going to have to use this first function, which means C of 30 is just 20. There's nowhere to plug in the 32. However, for the 100, because that is bigger than 60, I now plug it into the second function. So this turns into 20 plus 0.4 times 100 minus 60. So that's 20 plus 0.4 times 40, which is 32. Whoops, not 32, sorry, 36, 36. 20 plus 60. If I wanted to, I could do this for any number. C of 40 would still be 20 because it's not bigger than 60. C of 80 would be 0.4 times 20 would be 28. Okay? So whatever number you pick, whatever number you're trying to evaluate, you need to pick which function to use. Okay, so let's skip down here to this problem that I did in class. Okay. The hardest part about this, evaluating this particular piecewise function, is to figure out which function to plug it into. So if I want to evaluate f of -2, I have to decide, is that less than -4 or greater than or equal to -4? And it is, of course, greater than or equal to -4. So f of -2 would be equal to 4 times -2 plus 2, which would be -6. Okay? And I use the second function down there because of the value of the variable. Okay? Now, let's graph some piecewise functions. Okay? So if you graph these correctly, you should have something that flows from this domain, and then the function switches to this one. If you do this wrong, first of all, we know that this is a line. Well, we'll make a table in a second. But if you don't do this right, you could have a line like this and a line like this. That would be the graph of these two different functions. But that's not what we want to do. Okay, so we want to only graph this function at this interval and this one at this interval. Okay, so if you're not sure what these are supposed to look like, maybe it's helpful to make a table. So first, x is less than or equal to 1. So I'm going to do x and y for 1, 0, -1, -2, -3. Okay, x less than or equal to 1. So if I plug that in, I get 3, 2, 1, 0, -1. And of course, as I start graphing this, I could use the rules of graphing a line, right? This is the intercept, that's the slope, and we would get 1, 3, 0, 2, -1, 1, boom, boom. And I would get a nice line like that. because this says less than or equal to, I'm going to put a solid dot on the end of that line, as opposed to this function, which would get an open circle. Okay. Now, I want x to be greater than or equal to 1, but 1 is really important because it's my boundary point. It's where one function switches to the other. So I still want to know what's going to happen at that particular point. Okay, so I still want to plug in 1, 2, 3, 4, 5, and greater than. Now realizing that whatever answer I get here is not going to be a solid dot, it's going to be an open circle. And of course, there's nothing to plug in here. All my answers are 4, which means I have a horizontal line. Let's make that a little bit better. We have a horizontal line traveling to the right. And that's what the graph of my piecewise function should look like. Okay, it has my first function there, my second function there. Okay? And I have graphed both pieces individually. Okay? We can find the domain. The domain of this function is all real numbers because we have coverage right there, and it passes the vertical line test, so this is a function. Okay. The harder thing to do is to find the range. The range is from negative infinity to 3, including 3, but notice how the function jumps over, and now it only includes 4, not an interval of 4. Okay, so it includes the interval from negative infinity to 3, union 4. Now this is a little bit easier to graph because it is 2 very simple functions. If we have some more complicated functions, it becomes a little bit harder. Okay, we'll get to exactly how to do this with transformations in the future, but for now, all you have to do is you can make a nice table for the first function. X is less than negative 3, so let's plug in negative 3. Even though it says less than and not less than or equal to, I still want to know where to put that point where it's going to switch from this function to this one. So negative 4, negative 5, negative 6, and if I plug that in, I would get negative 3 plus 4, that's going to be 1, 0, 1, and then 4. Yep, okay, so for the next one now, the next one gets a little tricky because I want to plug in negative 3, negative 2, negative 1, 0, and so on, and then let's plug in 3, and we'll see why in a second here because it's a radical. But if you try to plug negative 3 into this function, it's undefined because you cannot take the square root of a negative number. So this is undefined, that's undefined, that's 0. If I plug in 0, that's the square root of 1. If I plug in 2, you get the square root of 3, which is kind of hard to graph, but if you plug in 3, you get the square root of 4, which is 2. And the boundary point, I'm going to need the boundary point, so that's going to be a little bit above 2. That's going to be radical 5. Okay? And then, of course, my last function, xy, I want to know what happens at the boundary point. So I want to plug in 4. Let's plug in 5. Let's plug in 6. So that's negative 4 plus 3. That's negative 1, negative 2, negative 3. Okay? And so on and so on and so on. So now I have enough data here, and all I had to do was make sure that I plugged the right, I plugged the numbers into the right function depending on the domain. Okay, and so now open circle, closed circle here. This is not going to matter because those two things were undefined, and open circle right there. Okay, so we got negative 3, 1 with an open circle, 1 done like that. So we get our we get our parabola, something like that. We have our radical function, which starts at -1, and boom, and then 3, 2, and it goes a little bit higher, right? Kind of hard to graph the square root of 5, but we'll do our best there. And 4, -1 with an open circle with my line going down. Again, later on in this course, we'll figure out how to do this using basic transformations without having to go through all of this tables. But for now, that's a good way to get going. Another interesting piecewise function is something called a step function. And these are called step functions because their graph form discontinuous steps. And one of these functions is called the greatest integer function, symbolized by int parentheses x, where x is your input, int is the function, right, the greatest integer function, or x inside these double brackets that look kind of like that. Okay, the way you calculate this is it's equal to the greatest integer that's less than or equal to x. So that means that if you take the greatest integer function of 1, you get 1, 1.3 you get 1, 1.5 you get 1, 1.9 you get 1. You always just round down. Here's what it looks like. Okay, so the graph of f of x equals the greatest integer of x is shown below. The graph of the greatest integer function jumps vertically 1 unit at each integer. However, the graph is constant between each pair of consecutive integers. The rightmost horizontal step of the graph shows that if -5 is less than or equal to x, which is less than or equal to 6, that's this one, then the greatest integer is 5. So in general, n is less than or equal to x, which is less than or equal to n plus 1, where n is an integer, then you have the greatest integer function. Okay? Okay? So this function is just kind of like a good to know and something that we'll use a little bit in the future, but not that much. In section 1.5, we're going to start studying average rates of change of functions. And this is a ratio, or there is a ratio called the difference quotient. And this is going to play an important role in understanding the rate at which functions change. The difference quotient can be calculated using this formula. So the expression f of x plus h minus f of x all over h for h not equal to 0 is called the difference quotient of the function f. Let's calculate a difference quotient. Well, back to this. This first part, f of x plus h, just means that you plug x plus h, replace x with x plus h in the function. Then you subtract the original function and you divide by a variable h. So let's first calculate f of x plus h, and then we'll put it down here into that function. Okay. So first, f of x plus h, here's my function, f of x. So I just replace x with x plus h minus x plus h plus 3. Okay. Now, I just got to clean that up a little bit, okay, because I can't leave it like that. So let's clean this up. Exponents come first. We have to FOIL this together, remembering, of course, that it has a middle term when I FOIL them together. So that's x squared plus 2xh plus h squared minus both of these. So distribute the negative, minus x minus h plus 3. Now I'm going to distribute out the 2 to give me 2x squared plus 4xh plus 2h squared minus x minus h plus 3. Now, we have our function of f of x plus h. I can't put anything together. None of them have like terms, so that's as much as we can do with that. So then I'm going to take this whole expression and subtract the original function and divide it by h. So let's do that. So we have 2x squared plus 4xh plus 2h squared minus x minus h plus 3, which was just this one right here. Did I get it right? Yeah, I think so. All right, so now we're going to take that minus the original function. The original function was 2x squared minus x plus 3. And because I'm subtracting the whole original function, I need to include these two parentheses. And what I'm going to do next, I'm going to divide everything by h, but what I'm going to do next is I'm going to distribute that negative. And if you do this right, okay, we can cancel out many of the terms here. So let's do this. 2x squared plus 4xh plus 2h squared minus x minus h plus 3 minus 2x squared plus x minus 3 all over h. Put any like terms together, 2x squared minus 2x squared, those two cancel. Minus x plus x, those two cancel. Plus 3 minus 3, those two cancel. And what we're left with is 4xh plus 2h squared minus h over h, which then have a common factor. The top has a common factor of h, 4x plus 2h minus 1 all over h, which now can cancel to leave me with my difference quotient of 4x plus 2h minus 1. Okay, let's try that again with another quadratic. Okay, so we'll find and simplify. I have my formula for my difference quotient right here, which I'll usually give to you. Okay, and let's plug in this is a very similar problem, so it should be pretty much the same steps. So we're going to calculate f of x plus h, so that's 2x plus h squared plus x plus h minus 1 minus the original function f of x. I'm going to distribute the negative as I go here, 2x squared minus x plus 1 over h. Same thing, FOIL first, so 2 times x squared plus 2xh plus h squared plus x plus h minus 1 minus 2x squared minus x plus 1 over h, and distribute the 2 to give me 2x squared plus 4xh plus 2h squared plus x plus h minus 1 minus 2x minus x plus 1 all over h. And if I did this right, whoops, if I did this right, 2x minus 2x plus x minus 1 plus 1, and then I'm left with 4xh plus 2h squared plus h over h. Factor out the h and cancel to give me 4x plus 2h plus 1, which is my difference quotient. Now, what we're going to do with these is we're kind of going to see what happens when this h value, and we'll talk about what that means a lot later, but we're going to see what happens when that h value becomes 0, and we would get 4x plus 1. Here, we would get 4x minus 1. But what happens if we have something really weird, like this? So let's calculate this difference quotient, and this is the last one. So let's find and simplify this difference quotient right here. So we have f of x plus h. So the first function is going to turn into x plus h minus 1 minus my original function, x minus 1 over h. Now I can't simplify any of this anymore because they're not like radicals. But the problem becomes here, if I want to plug a 0 in for h, I can't do it in this expression because that would just give me a 0 in the denominator and it would be undefined. So what I'm going to do is I'm going to rationalize the numerator, which is we practiced this a little bit in an earlier section. but let's multiply the top and the bottom by the conjugate of the top. So that gives me x plus h minus 1 plus radical x minus 1 over x plus h minus 1 plus radical x minus 1. Now, when I FOIL these together, right, the middle terms are going to cancel out. That's the point of multiplying by the conjugate. And we're left with a radical times a radical, so the radical just goes away. So we're left with x plus h minus 1 minus both of them, right, x minus 1 all over h, whoops, that's too far, h times this plus this. So we're just going to leave that non-multiplied together, x plus h minus 1 plus the square root of x minus 1. Right, that's all I did, right? I'm just distributing the h to both of them. Now, because I got rid of all these radicals up top, I can simplify this into x plus h minus 1 minus x plus 1. The 1's cancel, the x's cancel, and so the top is just h over all of this stuff, h times x plus h minus 1 plus radical x minus 1. Yeah, a little squish there. But the point is that those two h's now can cancel, and I'm left with, my difference quotient of 1 over the square root of x plus h minus 1 plus the square root of x minus 1. And now if I wanted to plug in 0 for h, which we're going to do later, I now have an expression that actually makes a little bit more sense and is not something that is undefined. Okay. And that was 1.3, more on functions and their graphs.